Hi there, my name is MisterCode, and in this video we're going to talk about mathematical induction. And before going into the details, let me first give you an overview of what we're going to talk about. So first of all, I will give an introduction to mathematical induction. I will tell what mathematical induction is, what it requires. I will also tell a brief story which is famous within mathematics and explain its relation to induction. And then I will visualize the idea of mathematical induction. Then we're going to talk about the principle of mathematical induction, which is a theorem, and I will actually prove it. Then I will explain how to create a proof using induction, and we will directly apply the step-by-step guide to two exercises, one involving a summation and the other one involving an inequality. And finally, at the end of this video, I will include two links to other videos that I've created on mathematical induction. One of them leaves out the details of mathematical induction and is just focused on how to create a proof. It also contains two different exercises, so if you want to practice a bit more with induction, you can have a look at that video. And another video contains 6 exercises, which I will prove together with you. So I think these two videos are a great opportunity for you to practice a bit more on induction. But for now, let's just introduce what mathematical induction is. So mathematical induction is a proof technique. It is used for proving that all elements of a set satisfy the same property. And this property can literally be anything. The only requirement is on the set, because the set has to satisfy the well-ordering property. And an example of such a set is the set of natural numbers. And the well-ordering property itself is an axiom. For the natural numbers, it is defined as the following implication. If a set S is a subset of the natural numbers and it is not equal to the empty set, then there exists an element L in S such that for all k in S, L is less than or equal to k. So imagine this using the following drawing. If this is your set, which is in our case S, and each orange dot represents k, then there exists a k which is L, and L is the least element of this set, because for every k, L is less than or equal to k. We use this element as the basis for induction. Without the well-ordering property, we couldn't use mathematical induction. So this is really an important property. And since the set of natural numbers satisfies the well-ordering property, as a result, mathematical induction is most commonly used to prove that all natural numbers satisfy a certain property. So let me now tell you a brief story, which is famous within mathematics. It is about Carl Friedrich Gauss, who lived in the 18th and 19th century. He was a German mathematician, and he was a born mathematician. The story goes that at the age of 8, one day he was in class, and his teacher thought he was annoying, so he gave Gauss a punishment. And the punishment was to add up all numbers from 1 to 100. So this seems like a terrible punishment. But within 30 seconds, Gauss went up to his teacher, and he said with full confidence, "The answer is 5050. And his teacher was stunned and a little confused. Would Gauss already know the answer because he had already done the computation? Or, well, what Gauss did was he saw a relation. Because if you add up the first element and the last element, you get 101. If you do the same using 2 and 99, you'll again get 101. And if you continue doing this until 50 and 51, if you add these two up, you again get 101. So the computation becomes actually quite easy. This is equivalent to saying that's equal to 50 times 101, which is of course 5050. So Gauss was really time efficient there. But the thing is, we can actually make this a bit more general, using the following formula, because we can formulate the following. For all n in the natural numbers, if we add up 1 plus 2 until n, this is equal of course to the sum of I is 1 to n over I, then this is equal to a half times n plus 1. And in Gauss's example, this was of course easy to show, but this is a far more general formula, and in order to prove this, we need something which is much stronger. Of course, we can just fill in 100 here, and we'll see that a half times 100 times 101 is the same as 50 times 101, and this is 5050. So for this example, this would be the right answer. But in general, if we have all n in the natural numbers, we need a strong technique. So that's where mathematical induction comes in, and therefore we can prove this using mathematical induction. This will be exercise 1. We will do this when I've explained the step-by-step guide to you. So this will be continued. The last thing that I'd like to tell you for the introduction is that mathematical induction is often compared to falling dominoes. And let me explain this to you. Well, if you have a sequence of dominoes, and this sequence is infinitely long, so you have infinitely many dominoes, then if you push the first domino, of course, in this drawing the first domino would fall to the right. And it's not just the first domino that will fall, but the second one as well, as it is pushed by the first one. And the third one would fall as well, because it's pushed by the second one. And the same will happen with domino 4 and 5. And if you have infinitely many dominoes, this would go on to infinity. And this falling to the right could be a property which we talked earlier about, which we could prove using induction. And as a comparison with mathematical induction, pushing the first domino is actually the basis for induction, in which you show that the first element of a sequence satisfies some property. And then if you choose an arbitrary domino from the sequence of infinitely many dominoes, and you assume that it will fall to the right because it has been pushed, and that it then will cause the domino that is next to the arbitrary domino to fall to the right, then you have your induction step. And assuming that the arbitrary domino will fall to the right is called the induction hypothesis. So the comparison makes sense. Let's now talk about the principle of mathematical induction. So the principle of mathematical induction is a theorem, and it's what mathematical induction is based on. Therefore, as a mathematician, it's important to know what a theorem is, and of course we have to prove it as well. So the theorem is defined as follows: let Pn be a statement that is either true or false for all n in the natural numbers. Then, for all n in the natural numbers, Pn is true if both P1 is true, and for all m in the natural numbers, if Pm is true, then Pm plus 1 is true. So this is really strong. It says that for all elements in the natural numbers, Pn is true, using these two conditions. So for the first element, some property holds, and for all m in the natural numbers, if Pm is true, then the element next to m satisfies the property as well. Now, if we'd like to prove this, we can do this using a proof by contradiction. So the theorem says that Pn is true for all n in the natural numbers. Let's now just assume that there exists an n in the natural numbers for which Pn is false. We'd now like to find a contradiction in order to prove that such a situation can't exist. In order to do so, we construct a special set S, where S contains all n in the natural numbers for which Pn is false. And as we've assumed that there exists such an n in the natural numbers, S can't be empty, because we have at least one element which satisfies the condition of S, that Pn should be false. Now, knowing that S is a subset of the natural numbers, as it's defined in that way, and that S is not equal to the empty set, based on the well-ordering property of the natural numbers, which, if you can recall, something which we've discussed earlier in the introduction, is an axiom that the set of natural numbers satisfies. And it says that if S is a subset of the natural numbers and S is not an empty set, so our constructed S satisfies these conditions, then there exists an L in S such that for all k in S, L is less than or equal to k. So there's a least element. So going back to our proof, we know that there exists an L in S such that for all k in S, L is less than or equal to k. This is just what follows from the well-ordering property. So now let's analyze this L that we have found. Well, using our theorem, we know that from condition A, P1 must be true. So L can't be 1, as L is an element of S, and S is defined as containing all elements for which Pn is false, and P1 is true, so L can't be 1. Therefore, L is greater than or equal to 2. Therefore, we know that L minus 1 is an element of the natural numbers, because it's greater than or equal to 2, so it's a safe thing to say that. And as L is the least element of S, L minus 1, which is of course less than L, is not an element of S, because L already is the least element, and if L minus 1 is less than L, it can't be an element of S, obviously. Therefore, because L minus 1 is not an element of S, PL minus 1 is true, else it would have been an element of S where Pn would have been false. So PL minus 1 must be true. Now if we apply condition B from our theorem to L minus 1, we know that as PL minus 1 is true, and from the implication it must follow that PL minus 1 plus 1 must be true. because we just substitute in the condition m by l minus 1. So this is what we do, and pl minus 1 plus 1 is of course equal to pl. Therefore pl must be true, based on the implication of our theorem. But now we have something strange. This is a big contradiction. So since pl is true, it can't be an element of S, because the condition in order to be an element of S is that pn should be false. But it is true, so L can't be an element of S, but we assumed earlier that L is an element of S. That's what we did over here. Therefore we can add a lightning symbol which represents the contradiction. And therefore, based on the reasoning that we have applied over here as a contradiction, and therefore our first assumption must be false. So there is no situation in which Pn is false. And therefore we can conclude that for all n in the natural numbers, Pn must be true. So QED, we have proved our theorem. Therefore, from now on we can use the principle of mathematical induction, which is really nice because that's what mathematical induction is based on. So now that we have proved the principle of mathematical induction, let's go to the step-by-step guide in which I will explain how to create a proof using mathematical induction. And I do this by the step-by-step guide that is in front of you. And this could be for the moment quite some information, but I assure you this is going to be easy, and we will apply the step-by-step guide with 2 more exercises. So I'm sure you will get what is written here, and it will just help you to create proofs using induction. So the 0th step is that the statement will be of the form: for all n in the natural numbers, Pn is true, where you can see Pn as some kind of function which gets as input an element or an object, and which returns either true if the element satisfies the property, or returns false if it doesn't. Then the actual proof begins, and the proof is divided into 2 steps, or into 2 parts. The first one is the basis for induction, and the second one is the induction step. Within the basis for induction, we show that the first element of the sequence satisfies property P. You can compare this with the sequence of falling dominoes, in which you push the first one, which will cause it to fall to the right. So here we just get the first element and show that the property for this first element holds. Then we move on to the induction step, starting with the induction hypothesis, in which we assume that for each n in the natural numbers, Pn is true. What we then have to prove is that for each n in the natural numbers, Pn plus 1 is true. So we assume that each n contains some property P, but we now need to prove that the next element next to n satisfies this property as well. In order to do that, we cannot just reason about n, because we're talking about for each n. Therefore, we have to choose an arbitrary n, and this has to do with the following. Because consider this drawing. If this is the set, which is in our case the set of natural numbers, and the orange dots represent all n, then it's more useful to choose an arbitrary n that's called k. And if we reason about this arbitrary k based on the fact that it's an arbitrary n, so all the other elements will have the same characteristics as k, we can conclude that if something holds for k, then it must hold for all n, since it was randomly chosen. So what we will do in step 5 is prove that pk plus 1 is true. And if we can do that, we can reason back to all n and conclude that pn plus 1 must be true. And showing that pk plus 1 is true is something which we do in step 6. And we do this using the induction hypothesis. You can see the induction hypothesis as some kind of a tool to help you prove that pk plus 1 is true. Then moving on to the 7th step, here we conclude that because we've shown that pk plus 1 is true, and as the implication pk implies that pk plus 1 holds for an arbitrary k, thus we can conclude that the implication Pn implies Pn plus 1 must hold for all n, based on the reasoning that I've just explained. Then we're ready for the conclusion of the proof, which is step 8. And in step 8 we say, thus, based on the principle of mathematical induction, the statement holds, which is a theorem, which we've just proved, so we're now allowed to use it. But this is the step-by-step guide. So now let's just apply it to the exercises that I've prepared, and during answering the first exercise I will refer back to the steps in the step-by-step guide. So the first exercise is the following one, and it's a familiar one since we've already seen this expression earlier when we were talking about Gauss over here. Here we deduce this formula, and now we're actually going to prove it. So it involves a summation, and the exercise is as follows. Prove that for all n in the natural numbers, the summation of i1 to n over I equals a half times n plus 1. So if you'd like to do the exercise on your own first with the step-by-step guide, then you're free to do so now. I think it would be really brave, so just pause the video and come back when you're done. But for now, I will just continue with the proof of the exercise. So this is the proof to the exercise. So in the proof using mathematical induction, we start with the basis where n equals 1. So we have our expression over here. We substitute n by 1 and we start at the left hand side and deduce what's on the right hand side. So first step, we sum from i1 to 1 over I, which is equal to 1, since we just sum over one term, which is I, where I is 1. So we have 1. This is of course equal to a half times 2. This is equal to a half times 1 times 2 of course. And we can rewrite this by rewriting the 2 as a 1 plus 1. And then we have exactly what's on the right hand side. So the basis step holds. Now moving on to the induction step. As the second step, we're going to need our induction hypothesis. So in the second step, we assume that for all n in the natural numbers, the sum from i1 to n over I equals a half times n plus 1. Simply the expression that's over here. What now has to be proved is that the sum from i1 to n plus 1 over I equals a half times n plus 1 times n plus 1 plus 1. Based on the reasoning that we've applied in the step-by-step guide over here, we have to choose an arbitrary k in order to reason about all n. So that's what we're going to do. Thus at step 4. So what has to be proved is then the exact same expression as over here, but now instead of using n, we use k. Then we start on the left hand side and we're actually going to deduce the right hand side. So we start with the sum of i1 to k plus 1 over I. Because we'd like to use our induction hypothesis, it's useful to split the sum up in the k plus 1 term and the sum of i1 to just k. So that's what we're going to do. The k plus 1 term drops out and is over here. And we have the sum from i1 to k over I. Now we can apply our induction hypothesis, which is over here. So we substitute the sum by a half times k plus 1. So that's now over here. We can rewrite this a bit because we have a k plus 1 term over here and over here, but a half times k. So we add the two terms, we get a half times k plus 1 times k plus 1. And what we will do now is extract a half from this term, and we will have a half times k plus 2 times k plus 1. And this, of course, we can rewrite again as a half times k plus 1 times k plus 1 plus 1. And this is exactly on the right hand side. So we've proved that. Then, as this holds for an arbitrary k, this must hold for all n in the natural numbers. And as a conclusion, since both the basis and the induction step hold, based on the principle of mathematical induction, the statement holds. QED. So, as you've probably noticed, the step-by-step guide requires quite some steps, but it gives you a nice overview of where you are in the proof, and it actually makes you understand what you're doing during the proof. So now that you understand this, hard work pays off. Let's now go to the second exercise, and the second exercise involves an inequality. What we'd like to prove is that for all n in natural numbers, 2 to the power n plus 1 is less than or equal to 3 to the power n. So again, if you'd like to do the exercise on your own first, you're free to do so. I can just encourage it, so press pause and come back when you're done. I will continue with the proof to the exercise. Oh, and by the way, as a hint, there is indeed an inequality in between. So during the proof, try to use this as a tool. Things don't have to be equal anymore. So this is our proof using mathematical induction. We start again with the basis where n equals 1. So we have our expression over here. We substitute n by 1 and we start at the left hand side and we work to the right hand side. So 2 to the power 1 plus 1 equals of course 3. And 3 is obviously less than or equal to 3 because 3 is equal to 3. And therefore we've introduced the less than or equal sign that we needed. And 3 is equal to 3 to the power 1. So we have what is on the right hand side. So the basis holds. Now our induction step. We start with the induction hypothesis, so assume that for all n in the natural numbers 2 to the power n plus 1 is less than or equal to 3 to the power n, which is just our expression over here. Now choose an arbitrary n in the natural numbers, we call it k. What has to be proved now is that 2 to the power k plus 1 is less than or equal to 3 to the power k plus 1, just what we had to prove earlier, but now using k instead of n. We start again at the left hand side and we're going to deduce the right hand side. So our left hand side is of course equal to 2 times 2 to the power k plus 1. Since we rewrite the exponent just a bit and make the plus 1 drop out, placed in front of the 2 to the power k. Well, this is of course less than or equal to 3 times 2 to the power k plus 1, because we add a 2 to the power k term, and we can apply the same trick with the 1. So this is less than or equal to 3 times 2 to the power k plus 3, so we add 2. And of course this is actually strict, greater than the previous expression, but since we only have to prove a less than or equal to expression, we don't really care about that. And we just write less than or equal to sign, so we don't have to prove something that is actually stronger than less than or equal to. Now we can extract this 3 and use our induction hypothesis, because that's what we're working to. So we have 3 times 2 to the power k plus 1. We apply our induction hypothesis, so we know that this is less than or equal to 3 to the power k. We fill in 3 to the power k, then we have 3 times 3 to the power k, and this is of course equal to 3 to the power k plus 1, which is exactly on the right hand side. And all signs in between are less than or equal to sign, so we have proved what needed to be proved for k. So as you can see, you can use the less than or equal to sign as a tool in order to use your induction hypothesis, and you're just a bit more free than in the case with an is equal sign with your operations. Now, as this holds for an arbitrary k, this must hold for all n in the natural numbers, and since both the basis and the induction step hold, based on the principle of mathematical induction, the statement holds. So again, QED, which we indicate with this little box at the end of the proof, of course. And as a conclusion, this proof wasn't really harder, we just had to get familiar with the inequality sign. Now, as the end of this video, I'd like to add 2 more links to more videos that I've created on induction. The one on the left is about, as I've already mentioned, on just the practical side of induction. So everything I tell in there is just sufficient to know to create a proof using induction. It doesn't contain the details of mathematical induction. And the one on the right contains 6 exercises which you can use in order to practice with creating proofs using induction. So I think it's a great opportunity for you to use these videos for further practice. But this is the end of the video. If you thought this video was useful, make sure to hit the thumbs up, to give this video a like. If you still have any questions, make sure to use the comment section. And if you'd like to see more of MisterCode, make sure to subscribe. So stay cool. Bye!